Welcome to the lesson on similarity. At the end of this lesson, you'll be able to identify similar figures and differentiate between congruent and similar figures. You will also be able to identify the conditions that define similarity of triangles and prove the basic proportionality theorem and its converse. You must be wondering why we're in a sports room during a geometry session. Well, there is geometry all around us. Let's try to find some here. Look at the different types of balls kept here. There's a football, a volleyball, a cricket ball, and a tennis ball. Ah, and here's a golf ball. That's quite a variety. All these balls are spherical in shape. Does this make them congruent? Objects are said to be congruent only if they are of the same shape and the same size. For example, look at these hockey sticks. They are equal in shape and size. Hence, they are congruent. As for the balls, though they are of the same shape, their sizes differ. Objects that are of the same shape but differ in size are said to be similar. Let's recap the definitions of congruent and similar objects. Congruent objects have the same shape and size, while similar objects have the same shape but may not necessarily have the same size. An important observation to note is that all congruent figures are similar, but all similar figures need not be congruent. Now, consider the geometrical figures given here. Let's sort the figures on the basis of similarity. Here, now all similar figures are aligned together. Let's analyze these figures to further understand similarity. All circles are of the same shape and their radii will always be proportional. Hence, all circles are similar. All squares are similar to each other as their angles are equal and their corresponding sides are proportional. Using the same logic, all rectangles are similar as the angles are equal and two pairs of corresponding sides are proportional. Now, let's check the similarity of triangles. On measuring the angles, we find that the corresponding angles are equal. On measuring the lengths of the corresponding sides, we find that the three pairs of corresponding sides are proportional. For two triangles to be similar, the corresponding angles must be equal and the length of the corresponding sides must be proportional. To better understand the property of the similarity in triangles, let's perform a small activity. Cut a triangular-shaped piece of cardboard. Let's call this triangle ABC. Now hold it between a light bulb and the wall. Can you see the shadow of the triangle? It is an enlargement or magnification of the cardboard triangle because light propagates in a straight line. Let's mark the shadow of the triangle as A', B', C'. Consider the point of the light bulb as O. Draw rays OA, OB, and OC originating from point O. If we extend this ray further, we'll observe that A' lies on ray OA, B' lies on ray OB, and C' lies on ray OC. This means that the triangles ABC and A', B', C' are of the same shape. However, their sizes are different. So we can say that triangle ABC is similar to triangle A-B-C- and vice versa. Mathematically, similarity is represented as shown. Here, vertex A corresponds to vertex A', vertex B corresponds to vertex B', and vertex C corresponds to vertex C'. Symbolically, these correspondences are represented as A', B', B', and C'. Similarly, angle A is equal to angle A', angle B is equal to angle B', and angle C is equal to angle C'. And all pairs of corresponding sides of the triangles are proportional. Note that the same ratio of the corresponding sides is referred to as the scale factor. Next, we will discuss an important theorem based on the similarity of triangles. This theorem is called the basic proportionality theorem or the Thales theorem. The basic proportionality theorem states that if a line is drawn parallel to one side of a triangle to intersect the other two sides in distinct points, then the other two sides are divided in the same ratio. A triangle ABC is given such that a line drawn parallel to side BC intersects the other two sides AB and AC at points D and E respectively. If we prove that AD upon DB is equal to AE upon EC, then the theorem will also be proved. To prove this theorem, join B to E and C to D. Also draw two perpendiculars, DM on AC and EN on AB. Let's begin the proof. Consider triangle ADE and triangle BDE. The area of a triangle can be calculated as half of the product of the base and the corresponding height. This means the area of triangle ADE is half the product of the base AD and the height EN. Similarly, the area of triangle BDE is half the product of the base DB and the height EN. Now, let's divide the areas of the two triangles. On simplifying, we can see that the area of triangle ADE divided by the area of triangle BDE is equal to side AD divided by side DB. Let's assign this observation as equation 1. Now consider triangle ADE and triangle DEC. The area of triangle ADE can also be calculated as half the product of the base AE and the height DM. The area of triangle DEC is equal to half the product of the base EC and the height DM. Now, let's divide the areas of the two triangles. We can see that the area of triangle ADE divided by the area of triangle DEC is equal to AE divided by EC. Let's assign this observation as equation 2. Consider triangle BDE and triangle CED. The area of triangle BDE is equal to the area of triangle CED because these triangles are on the same base DE and between the same parallels BC and DE. Let's assign this observation as equation 3. From equations 1, 2 and 3, we get the following expression. This implies that the ratio of sides AD and DB is equal to the ratio of sides AE and EC. Thus, the basic proportionality theorem is proved. Now, let's prove the converse of the basic proportionality theorem. The converse of the theorem states that if a line divides any two sides of a triangle in the same ratio, then the line is parallel to the third side. Consider the figure. A triangle ABC is given. The line DE intersects side AB and AC at points D and E respectively, such that the sides are divided in the same ratio. To prove the theorem, we'll prove that line DE is parallel to side BC. In triangle ABC, AD upon DB is equal to AE upon EC, because it is given that line DE intersects the sides AB and AC in the same ratio. Let's assign this observation as equation 1. Let's assume that DE is not parallel to BC. If DE is not parallel to BC, draw a line DE' parallel to BC. Since DE' is parallel to BC, by the basic proportionality theorem, we have AD by DB is equal to AE' by E'(C). Let's assign this observation as equation 2. From equations 1 and 2, we get AE by EC is equal to AE' by E'(C). Let's assign this observation as equation 3. Adding 1 on both sides of 3 and on simplifying, we get EC is equal to E'(C). Therefore, we can say that E and E' coincide. Hence, DE is parallel to BC.